Hi, so this next video is being split into two parts. The first part will work through the first half of a problem building up to a collision. The second part will look at the result after objects have collided and stuck together. And this problem examines conservation of energy concepts and conservation of momentum, specifically conservation of angular momentum. So in the problem, there's a mass that's at the top of a ramp some distance h above the ground. It slides down the frictionless ramp and collides with a bar that has a length of d and a mass of m, and it sticks to the end of that bar. So if it collides and sticks, that bar is going to rotate and eventually it'll come to rest. So we actually have two conservation of energy problems in addition to the conservation of angular momentum. So we'll take a look at the conservation of energy problem for the first part, and then look at what happens with the collision. And in the second part of this video, we'll take a look at what happens after the collision when those objects are stuck together. So, for the first part, if an object is sliding down a ramp, we can, as long as we can ignore friction, we can just look at the types of energy. So if it's stopped at the top, we'd say the kinetic energy of that object is 0, and the potential energy of that object is going to be the mass of the object times gravity times its height above where we call our zero potential energy point. And that zero potential energy point, let's make it the bottom of the ramp. Now the shape of the ramp doesn't matter, because with energy, doesn't have any direction with the problem. So, as long as that ramp has any shape whatsoever, whichever direction it would be traveling at the bottom, we'd still be traveling at the exact same speed. So down at the bottom, we said we have zero potential energy, but our kinetic energy is going to be 1/2 times the mass that's on the ramp times the speed of that mass at the bottom of the ramp. So if I set the potential energy at the top equal to the kinetic energy at the bottom, 1/2 mv squared is equal to mass times the strength of gravity times the height, we get the result, after canceling out the mass on the ramp, that the speed of an object that falls a distance h, this is general, is the square root of 2 times the strength of gravity times the height that that object fell. Now, once we know that speed, we can look at the collision. And with any collision, we treat collisions like isolated systems. And in any isolated system, there's no outside force, there's no outside torque, momentum and angular momentum are conserved. So, in this problem, this mass sliding along the ground technically has linear momentum. But with angular momentum, all objects with linear momentum have an angular momentum, because the angular momentum is the radius of rotation crossed with the linear momentum of an object. So if we treat that mass as being like a particle, its radius is just going to be the length of our bar, d. So that means that the angular momentum of that mass is going to be our distance d times our mass times our velocity at the bottom of the ramp, which means the angular momentum of that object is the distance, the length of the bar, times the mass that slid down the ramp, times the square root of 2 times the strength of gravity, and the height that that mass started above where that collision happens. And since momentum is being conserved, specifically here angular momentum, the initial angular momentum equals the final angular momentum. Now, after the objects collide, they stick together. Well, this is a completely inelastic collision. So in a completely inelastic collision, we have one object afterwards. So my final angular momentum is just the rotational inertia of that single object times the angular velocity of that object, omega. So if we want to calculate omega, we need to calculate the rotational inertia of this combined mass system. Well, when we have more than one part, we can always find the total rotational inertia by adding the inertia of each piece together. So with this system, I have a particle at the end of that bar, so the inertia of that mass would just be the mass times the length of the bar squared. For the inertia of the bar, it's pivoting around its end, so for a bar pivoting around its end, the inertia is 1/3 times the mass of the bar times the length of the bar squared. Well, one of the things to note, both of those depend on the length of that bar squared. So we could factor that out from our inertia. And our final angular momentum is our initial angular momentum. That depends on the length of the bar. So there's the length of the bar in the numerator, there's a length of the bar squared that would be in the denominator. So when I divide my initial angular momentum by my moment of inertia of the combined object, I get an angular velocity that's equal to the little mass times its velocity at the bottom of the ramp, the square root of 2 times the strength of gravity times the height, and that would be divided by the little mass plus third the mass of the bar times the length of the bar. Thank you for watching part 1, and in part 2, we'll take a look at the problem starting with this angular velocity and figure out how far that bar is going to rotate to calculate the ultimate angle.